Hello, this is an extension to lesson 2.2.4 about graphing non-functions and using transformations in order to generate their graph. And the extension is that really we're going to look to figure out where do these two functions, again the top function is a circle and the bottom function right here is a parabola. Where does the circle and the parabola, where do they intersect? We're going to try this graphically first. The first thing I need to identify is, again, the graphing form of a circle is x minus h squared plus y minus k squared equals r squared. And so the center of the circle is very valuable. I can see there's no horizontal shift. So the center, which is your key locator point for the circle, is at 0, in this case 1, and the radius is the square root of this particular constant. And so the radius here, r, is equal to the square root of 25, and the square root of 25 is 5. And so this is how I can generate the first part of my graph, which is the circle. Thinking about a transformation up 1 unit. So I'm going to go ahead and just kind of draw a quick little dashed line. This represents the shift up. It's a vertical shift up. I'm drawing a horizontal line, and that horizontal line really represents the x prime axis, the transformation. After that, I'm really just graphing the parent graph of this circle with radius of 5. So again, if this is the circle center right here, 0, 1, you're counting up 1, 2, 3, 4, 5. To find a point there, you're counting over 1, 2, 3, 4, 5. You're counting down 1, 2, 3, 4, 5. And you're counting this way from here, that's the center, 1, 2, 3, 4, 5. And that's the radius. That's only 4 points. And yesterday in the lesson, hopefully you recognize you could use right triangles, a 3, 4, 5 Pythagorean triple, to find more points without a table of values. Meaning I can count over here 1, 2, 3 and up 1, 2, 3, 4 to find another point right here. Okay, likewise, we could have a triangle with side 4, 1, 2, 3, 4, and height 3, 1, 2, 3, to find another point. So this is how we use right triangles. Again, this is the radius here. Again, there are infinite number of radii that extend from the center of the circle to the outside of the circle. And that allows me to have more points, and so my graph is nice and circly. And now we can do the same thing in the other quadrants. So likewise, 1, 2, 3, up 1, 2, 3, 4, and out 4, 1, 2, 3, 4, up 1, 2, 3. So again, this is really a reflection over here, and now I got more points, so my circle is turning out beautiful. 1, 2, 3, 4, down 1, 2, 3, and likewise 3, 4, and so there are more points. And I can connect all of these. And likewise 1, 2, 3, down 1, 2, 3, 4. And again 1, 2, 3, 4, down 1, 2, 3. So I'm using right triangles. The radius of the triangle is the hypotenuse of the right triangle. And that hypotenuse is the radius of the circle, which is again 5. And now look at that amazing circle without even using a compass. For the next graph, the graph of, in this case, it's a parabola, and that parabola, it's been shifted down 4 units. So recognizing this is in a graphing form as well, the parabola. I'm going to graph it in a different color. And as a reminder, it's y equals, you would have an a value, but it's x minus h squared plus k. So your vertex really here has not been shifted at all horizontally, but it's been shifted down to -4. And so look at, I already see graphically a point of intersection right here at 0, -4. The circle and the parabola have a common point. And then, since again I've shifted my whole function down, this is really the transformed axis for the parabola. And then I'm plotting the parent function since there's a stretch factor of 1. So 1 unit to the right and the left of the vertex, it grows by 1. Again, that's the beginning of the parabola. 2 units to the right grows by 4, 1, 2, 3, 4, so I can find an x-intercept. Likewise, there'll be a point that's equally far away from the line of symmetry. So I've got more x-intercepts, but those are not points of intersection, okay, for the parabola. And then 3 units to the right, 1, 2, 3, I travel up 9. So 1, 2, 3, 4, 5, 6, 7, 8, 9. Oh my goodness, I found another point of intersection there. That point right there is 3, 5. 3, comma 5. Likewise, 1, 2, 3, and then up 9. So I can either count 9 or recognize, since this is the line of symmetry for the parabola, and there's a point 3 units to the right, there'll also be a point 3 units to the left. And so that's how I get my other point of intersection here, which is at negative 3, 5. And I'm going to label that a POI for a point of intersection. Notice there are 3 points of intersection for this particular non-function, being the circle and the function. So that completes the graphical way of solving this problem. Please tune into the next video. The next video, I'll show how to do this algebraically.